Good morning, friends. In last lecture, we have seen the design steps for analysis and design of bolted joints for axially loaded plate, single and double angle members. In that steps, we have calculated in step first the strength of bolt in shearing, then strength of bolt in bearing, then bolt value, and then number of bolts required and its sketch. On that basis, on that design steps, we are going to see one problem. Here is a first problem on that. Suppose a problem is given like this: design the lap joint. Here is lap joint is given. Lap means two plates are overlapped on each other. One plate is over the other. Design the lap joint for two plates. Here two plates are given and those plates are 120 mm into 6 mm thick, both having the dimensions one plate 120 mm by 6 mm thick, another plate also of the same size 120 mm into 6 mm thick. These are the two plates and these are connected with lap joint. To transmit, that is, this connection must transmit a load of 150 kilonewton, and this load is given as factored load. Using single row of, we have to use the single row of bolts for this connection, and the bolt diameter is given as 16 mm, that is 16 mm diameter bolts of 4.6 grade. That is, grade of bolt is given here. In last lecture I have given regarding this grade 4.6. When the grade is given as 4.6, then ultimate stress in bolt is calculated as 4 into 100, that is 400 Newton per mm square is the FUB, and plates, that is plate grade is given as 410 Newton per mm square, that is ultimate stress in plate, that is FU is given as 410 Newton per mm square, and FUB, that FUB is equal to 4 into 100, that is 400 Newton per mm square. We have to take while solving the problems. See here, we have to design a lap joint for two plates. These two plates are 120 mm into 6 mm. Another plate is also of the same size 120 mm into 6 mm. These two plates are to be connected by lap joint by using 16 mm diameter bolt. This diameter of bolt is given as 16 mm, that is this diameter is a nominal diameter, that is this diameter before bolting, before doing the connection, that diameter is nominal diameter, and the bolt grade is given as 4.6 and plate grade is given as 410 Newton per mm square. So first we have to consider the given data. See here, in given plates of size 120 mm by 6 mm, these are the plate size. Thickness of plate T is 6 mm, that is 120 into 6, 6 is mm is the thickness. This is the thickness of plate is 6 mm. Diameter of bolt, that is nominal diameter, you can write as D or D suffix N, nominal diameter DN is equal to 60 mm. Bolt grade 4.6, and we have to find the number of bolts. That is, the design means nothing but we have to calculate the number of bolts required. Okay, so we have to find the number of bolts for this lap connection, for this lap joint. So the basic data here is diameter of bolt hole, that in last lecture I have given the notation regarding this. This diameter, the bolt diameter, given diameter is a nominal diameter. That nominal diameter is the diameter of bolt before bolting, and gross diameter or whole diameter is the diameter of bolt after bolting. So some clearance should be added to calculate the hole diameter or bolt hole diameter, so that in this nominal diameter we have to add 2, that is from 12 mm to 14 mm. When the nominal diameter is 12 mm to 14 mm, then we have to add the clearance as 1 mm. But when the bolt diameter is from 16 mm to 24 mm, then we have to add the clearance as 2 mm, and above 24 mm nominal diameter we have to add the clearance as 3 mm. So here bolt diameter, nominal bolt diameter is given as 16 mm, so add the clearance as 2 mm, that is whole diameter or gross diameter. It can be denoted as DG, that is gross diameter. This can be denoted as DN, that is nominal diameter. That is gross diameter is equal to DN, nominal diameter, plus clearance, and that clearance is 2. So total hole diameter or gross diameter is 18 mm. So then calculate the area of bolt. The area of bolt is calculated considering the nominal diameter of the bolt, that is pi by 4 into d square. Since bolt it is given as a diameter, its area is pi by 4 d square, that is equal to 201.06 mm square. Now net area of bolt, that is ANB. This net area, see here, this area of bolt is shank area. Shank means its bottom area or at the top diameter area. This area is more. After bolting, the net area of bolt is reduces, and that reduction is taken as 0.22 of ASB. That is, we have to take only 0.78 into ASB. That is ANB, net area of bolt, is 0.78 into 201.06, that is 156.83 mm square. This is the ANB. So while solving the problems, you can directly calculate the net area of bolt as 0.78 into pi by 4 into d square. Directly you have to take. You don't consider this area of bolt at ASB. Don't calculate this one. Directly go net area of bolt ANB is 0.78 into pi by 4 into dn square. Dn is the nominal diameter. From that you have to calculate A and B. This value is required while solving the problems. Then pitch. This pitch should not be less than 2.5 dn. Dn is the nominal diameter of D. You simply say as D, or dn is the nominal diameter. Here nominal diameter is given as 16 mm, that is 2.5 into D, that is 2.5 into D, that is diameter of bolt 16 mm, that is 2.5 into 16, that is equal to 40 mm. So we have calculated the pitch, we have calculated A and B, that is net area of bolt, we have calculated the hole diameter or gross diameter as 18 mm. These are the required values. Then edge distance. This edge distance should not be less than 1.5 d0. See here, this edge distance, in last lecture I have given the edge distance. Edge distance is nothing but it is the distance from one edge of the plate to the center of the nearest bolt. That distance is edge distance. This edge distance should not be less than 1.5 d0, that is hole diameter or gross diameter. That is 1.5 into gross diameter is 18 mm, that is 27 mm. Say you can increase this diameter or round up this figure as 30 mm. Don't round to least value, that is 26, 25. You have to add more, that is 27 mm to 30 mm. Then grade of bolt is given as 4.6. So ultimate stress in bolt, that is FUB, ultimate stress in bolt. U for ultimate, F for stress, and B for bolt. Ultimate stress in bolt is 4 times of 100, that is 400 Newton per mm square, and yield stress in bolt FYB is equal to 0.6 into this ultimate stress in bolt, that is 400, that is 240 Newton per mm square. And partial safety factor for ultimate stress, that is gamma m1, is 1.25. This value is fixed, and the Fu is given as 410, that is ultimate stress in plate, that is 410. Now in this problem all the values we have taken, that is we have calculated the gross diameter or hole diameter, we have calculated the net area of bolt, we have calculated the pitch, we have calculated the edge distance, then we have calculated the FUB, that is ultimate stress in bolt, we have calculated the partial factor of safety. All these values we are going to use in the next step, that is step number 1. In that, strength of bolt in shearing, that is VDSB. That formula is, in last lecture I have given the steps regarding this, that is VDSB is FUB upon root 3 gamma m1 into NN into ANB plus NS into ASB. And in last lecture I have given this value of NS as 0. So this total value becomes 0. So NN, number of threads which are intercepting in shearing, that is equal to 1 for single shear, and ANB, net area of bolt, we have calculated. Put all these values here, that is FUB we have calculated as 400, root 3 gamma MB as 1.25, NN as 1, and ANB as 156.83 mm square. From that you have to calculate single shear plane, that is we have to calculate the strength of bolt in shearing, and that is equal to 28.97 into 10⁻³ Newton, and that is equal to 28.97 kilonewton. Delete this 10⁻³, the answer is 28.97 kilonewton. Then in second step you have to calculate strength of bolt in bearing. For that the formula is VDPB is equal to 2.5 kb into D into T into Fu. Here kb is the bolt constant, and it is taken the minimum of these 4, that is first value is E upon 3d0, second value is P upon 3d0 minus 0.25, and third value is FUB upon FU, and fourth value is 1. These are the values. Now D is the nominal diameter, T is the thickness of plate, Fu is the ultimate stress in plate, that is given as 410, gamma MB is taken as gamma m1, that is 1.25, that is partial safety factor for ultimate stress. Put all these values in this formula. So while putting the values you have to calculate the value of kb, that is bolt constant. In that first value E upon 3d0, E is the edge distance, and this edge distance should not be less than, this edge distance should not be less than 1.5d0, that is 30 mm. It should not be less than 30 mm. So E is equal to 30. D0, that is hole diameter or gross diameter, that is given as 18. Calculate this value and this will be equal to 0.55. Then second value P upon 3d0 minus 0.25, that is equal to P. P is the pitch and it should not be less than 2.5 dn or D, that is the nominal diameter, and it is its value is 40 mm. So put this value here. D0 is 18 mm minus 0.25. Put all these values and calculate the value of this. Then third value is FUB upon FU, that is FUB ultimate stress in bolt is 400 and FU ultimate stress in plate is 410. It is written wrong, printing mistake is here. That value is 0.97. So from this all these values, the value of minimum value of kb is 0.49. least value, we have considered the least value, this value is least value, and that is 0.49. So put the value of 0.49 here in this formula. Kb is 0.25, D is the nominal diameter, that is equal to 16 mm, T is the thickness of plate 6 mm, Fu is the ultimate stress in plate, that is 416, and gamma mb 1.25. Put all these values in this formula and calculate the bearing strength, and that is equal to 38.57 kilonewton. So we got two values, one shearing strength, and that is 28.97 kilonewton, and second one is 38.57 kilonewton. Here also a printing mistake. You have to consider 28.97 kilonewton, not into 10 raised to 3. 28.97 kilonewton, and this bearing strength is 38.57 kilonewton. In that, the minimum value, that is shearing and bearing, the minimum value is 28.97 kilonewton. That is that minimum value is known as bolt value. So the bolt value is taken as 28.97. So bolt value, minimum strength of shearing and bearing, and that is equal to 28.96. Here again printing mistake is there. You have to take 28.97 kilonewton. And in that fourth step, number of bolts required. Number of bolts equal full strength of bolt, that is given load in the problem. That is, we have to design this connection, lap connection, for a load of 150 kilonewton. That is the full strength of the bolt, that is 150 kilonewton. That is given load divided by the bolt value, and this bolt value is least value, and least value is 28.97. So put here 28.97, and that value is 6 number of bolts. From that, we have to sketch the diagram. Here is the first plate, and on that a second plate is provided at upper side. This is top plate, and this one is the bottom plate. Since a dotted line is given here, this is the upper plate and this one is the lower plate. And number of bolts required are 6 numbers, 6 bolts of 60 mm diameter, and these plates are of size 120 into 6 mm. This plate is also 120 into 6 mm, and the edge distance, minimum edge distance is 30 mm, and we have calculated the pitch as 40 mm. That pitch is nothing but it is the center to center distance between two adjacent bolts, and edge distance is the distance from center of bolt and the nearest edge of the plate. This distance is edge distance. Similarly, here is also a edge distance. So draw a sketch. This is the plan, this is the section, cross section or front view. In front view you can see this is the upper plate, this one is the lower plate, and this is connected by 6 number of bolts. This is the sketch. So likewise you have to solve these problems. So once again, first go through the steps. In that steps you have to calculate the bearing strength, then shearing strength, or you have to calculate first shearing strength and then bearing strength. Anywhere you have to calculate. That is, first calculate the strength of bolt in shearing, then strength of bolt in bearing, and then the minimum of these two gives you the bolt value. Then after getting the bolt value, you have to calculate the number of bolts. So to calculate the number of bolts, you have to take the design load which is given in the problem, divide this design load to the bolt value, you will get the number of bolts, and through those number of bolts you have to show the connection, how you have connected these two plates. This is second plate, this is one first plate, and you have connected these plates by 30 mm edge distance and 40 mm pitch, and this is the section, or this is the front view. You can show like this. This is sketch of that problem. So this problem gives you 6 marks. So friends, start with these such problems. Then here step number 5, you have to check the strength of plate. This strength of plate checking is required because when we are going to provide those number of bolts we are designed for that 150 kN load, then this plate with this bolted connection can be safe or not. So that we have to check for the strength of plate. So for that checking of the plate strength, use this formula, that is TDN, design strength in tension, that is 0.9 AN FU upon gamma M1. AN is the net area, FU is the ultimate stress of plate. Then net area in section normal to force is, area is nothing but is width into depth. So here is the width into depth, that is D0, that is whole diameter into thickness, that gives width of plate, size of plate is 120 minus D0 18 into thickness of plate 6, that gives the 612 mm square. Then TDN, that is design tensile strength of plate, is 0.9 AN. AN is the net area, FU plate stress 410, and gamma M1 1.25, that gives the 180.66 into 10 to 3, that is 180.66 kilonewton, that is it is the strength of the plate. And we have to calculate, it should carry a load of 150 kilonewton. See here, this plate carries a load up to 180.66 kilonewton, and we are only going to apply 150 kilonewton load. So these plates are safe for the carrying the load of 150 kilonewton. This data is not required, but remember this one, you also go through this check. Design strength of the plate from yielding consideration, that is gross, here you have to consider the gross area only, that is Ag into Fy upon gamma M0, and gamma M0 is the partial factor of safety, that is taken as 1.1. These values are given, that is Ag gross area, that is 120 into 6 into 250. 250 is the yield stress. We are considering the yielding stress consideration, that is yield stress. The stress into area, that gives the force, that is Ag into Fy upon 1.1, that gives the total 160.64, which is greater than load carrying capacity of 150 kilonewton. So this plate is safe for carrying the load of 150 kilonewton. So provide this design. In next problem, you don't carry this step number 5 or this yielding consideration, because only we have to require up to the sketch. Only I have given this step to check when you are going to become an engineer, and you have to check that these plates should sustain the load or not. For that purpose, you must remember this one. Okay, thank you.